So I think we're going to switch up the format a little bit. We're going to do announcements at the beginning, just so, in case we don't get to the technical content, we don't get to it, but we at least get to the announcements. So there's a guest lecture on Monday. This one is so apologize, we're going to be switching, I think for the next month, I think through the end of October, some lectures are going to be remote, some lectures are going to be in person, partially because of sort of guest lecture availability, where they are physically, and partially because where I am physically due to travel. So I'm going to try to be very careful with sort of like sending y'all links and so on. But Monday's guest lecture is going to be remote. It's going to be via Zoom. Sort of please attend live remotely. I'll send out the Zoom link to everyone via EdSTEM over the weekend to make sure everyone can attend. But so there's that. I've released quiz 1 on Canvas this morning. It's available until Friday evening. You'll have 1 hour to complete it. Open notes, open homework. I sent an announcement with some details. Please don't post any questions on EdSTEM about the quiz until like next week, just to give everyone a chance to do it.
How long should we estimate it'll take, just so I plan appropriately?
I mean, I don't like giving estimates. You have an hour. I don't think you'll need that entire hour, but you have an hour, and so you should, to be safe, you should block out that time. Homework 2 has also been released. It's due Tuesday, October 5th. There's that. And then this morning I also posted a homework buddy form. Some of you asked to either be partnered with other people or sort of just like to know who else wants to do homework with other people. So if you're one of those people who just wants a homework buddy to just discuss the homework or just like sit next to each other and work on it, please fill out that form. On Saturday, please fill it out by Friday night. On Saturday morning, I'll make sort of everyone who answered that sheet, I'll make that sheet available to everyone who answered. So you can, and then from there, you all can take it and sort of go from there to find a buddy. There was also, I think, some confusion on the homework collaboration policy. Sort of in the survey, you're not limited to talk to just one person on the homework. You can talk to as many people as you want. You can talk you can discuss in detail as much as what you want in the homework. You can sit together and like discuss each question and do it. Sort of what I don't want is you just email your solutions to someone and like they copy it out and turn it in. I was a student not so long recently. Like I think most people are aware of where's the line of like discussing and collaborating and like, helping each other with code and like straight up copying. So like, don't cross that line, but, very much encourage discussing and like, working together on the homework with other people. Are there any questions about that? Okay. Cool. Okay, so are there any questions about any of the announcements, course logistics, anything? Okay, then let's get started. So it's been a week, so I'll give you sort of a summary of recommendations. So last time, and before we continue, so last time we talked about the prediction, or we started talking about the prediction part of recommendation systems, right? So you have a bunch of data that looks like this. We can, for now, let's ignore where that data is coming from, whether it's implicit ratings or explicit ratings or whatever. But you have a matrix that looks like this, where you have users on the rows and then items on the columns. And then you have some data, which is how much some users like some items. And the goal is to fill in this matrix, is you want to predict what the missing entries look like, right? So like how much will Alice like Lord of the Rings if she watches it. And then last time we ended on briefly talking about matrix factorization. Models are also called latent factor models. Also is called a type of collaborative filtering recommendation systems. And this is what we're going to focus on in the homework, is these type of models. I'm not going to ask you to train them, but I'm going to ask you to use the outputs of a trained model. So here we have a d-dimensional. So like, for example, in this image, d is 2. A d-dimensional vector for each user, and a d-dimensional vector for each item. So ui for each user and vj for each item j. And we train these vectors. Sort of this class is not about training prediction models, so I'm not going to really get into how to train it. But suppose we train these vectors such that the dot product equals the rating, like sort of the dot product of these two vectors for every I and j equals the rating data, sort of approximately equals the ratings data in the training data. Right, so this is, we train it somehow such that this is true. And then how we fill in the rest of the entries in the matrix is we say that we're going to predict that the rating that everything is missing is just the dot product for user I, for the user's I vector with item j's vector. Right. So as an example, so this is the matrix that we have, the ratings matrix, and then we can we approximate it by sort of a user vector, a user matrix and an item matrix. And how to read this matrix is each user is a row. And so we have 2 dimensions. And so this first row is user 1. And so their vector is 0.1 and negative 0.4. And then in this matrix, each item is a column. And so to read this is item 1 or item 0, depending on how you like to do your indexing, is 1.1 and negative 0.7. And so the predicted rating, so, you know, a 1 is filled in, and so this was already in the data, but a predicted rating for this first user and first item is going to be 0.1 times 1.1, which is 0.11, times negative 0.4 times, or plus negative 0.4 times negative 0.7. So that's positive 0.28, right? So the predicted rating for this first user and first item is 0.39. And then sort of we can keep going. And so you know, 0.5 times 0.8 is 0.4, plus 0.6 times 0.2 is 0.12. And so the predicted rating for the second user and second item is filled in here. It's at 0.52.
That's a good question. The dimension D, is that sort of like a hyperparameter of the training process?
Oh yeah, so the question was, oh, oops. So the question was, is dimension D hyperparameter of the training process? Yes, right? So you're gonna choose dimension D for like, I mean, based on how much data you have and based on like how complicated you you like what dimensional space you think the world lies in. So sort of, you know, I know this doesn't provide great intuition, but suppose the ratings matrix was a rank D matrix, right? So sort of some of you with, you know, maybe more of a linear algebra background than others is you would recognize that if this matrix was a rank D matrix, then if you set D to the rank of the matrix, then you could actually recover the matrix exactly, right? So you could sort of, with less data, but with D dimensions, you could actually, with enough entries filled in, you could actually recover the exact matrix. So there would be no errors. But if D is smaller than the rank, then you can't do that. There's going to be errors. Even if you had as much data as possible, it physically would not be possible to represent the entire matrix.
I suppose we were kind of do the dotting the first row and the first column there. So is the matrix on the left like the result of a product, or are we trying to predict, or is that like our prediction for that matrix?
Yeah, good question. So the sort of what I intended here is, so this matrix, like so you can pretend the 1s and 0s are like your training data, right? So you had some training data, and then somehow from that training data you construct these users vectors and item vectors. I'm not going to go into this class and how you do that, right. But and then from then now you have this. You're going to use this to fill in all the remaining entries, right? So for example, we filled in this yellow box of 0.52 from like the corresponding second item and second user and second item. And so we can do sort of conduct the same exercise for every other missing entry.
Got it. So the first row and first column dotted, that's like a prediction for that one.
Yeah, well, yeah. So exactly. So like we filled in a 1 here because that was already in our training data.
Yeah.
But if we wanted to override it from what our prediction would be, it would not be a 1.
Right.
We would predict it to be like whatever. What did I say? 0.38 or something along those 0.39. And so if you carry this exercise out for like the entire sort of matrix where all the sort of the entries are already filled in, if this did a good job, if the training process did a good job, then you should find that the predicted ratings correlate with the training data, right? So if it's a 0, it should be smaller. If it's a 1, it should be higher. Any other questions on matrix factorization? So in the homework, we're going to give you a bunch of these sort of vectors. So we're going to give you like the outputs of this training process for different kinds of like training data used, like whether it was implicit ratings or explicit ratings processed in various ways. And then we're going to ask you to sort of fill in the entire matrix with predictions and then to make recommendations from those predictions. And so before I move on, I really want to make sure people understand how to use sort of how to make predictions from these outputs. Okay, great. And then I hope sort of either in a class like applied machine learning or some other class that you take, you really dig into how to train these prediction models, how to train these user and item vectors. Okay. And so as an example, here's something that I'm not sure, but I might have showed this last time, where like, we train vectors for a bunch of movies, and then we can plot them on 2 dimensions. And this is kind of misleading in that there's no reason that the dimensions are interpretable in this manner, right? So in this plot, you can interpret like the first dimension, the X, sort of the horizontal dimension as being children to adult movies. You can interpret the vertical as like blockbuster popular versus like niche art. But there's no reason that like this is true, right? If I just rotated the entire plot by 45 degrees, that is an equally valid output of the training process. Sort of that actually would lead to the same loss function. And so like that's, equally likely as this thing happened. But just as an example, you can, here's like sort of where movies could lie. And then what's nice about this is sort of movies lie at this space, and then sort of customers can also lie in the same space. So you can put, maybe I'm someone who likes, blockbuster children movies, and so like I'll be here. And so it'll predict that I really love The Incredibles and Shrek, but I'm not a big fan of, not even heard of some of these movies, Waking Life. And it will do that for each user as well. Sort of each user will also be placed in this 2-dimensional space, and they'll be not physically, they'll be near in the space movies that they're predicted to like.
So I see in the matrix algebra why you have the same hidden dimension for both like the items and the users, but let's say you maybe have a feeling you can model movies higher dimensional space. You don't know that much about your users, so it makes sense. Like, is there a way to have varying dimensions?
Yeah, so the question is there a way to have varying latent dimensions and still do something like this? So, I mean, in this framework with like a matrix factorization based framework, where the predicted rating is the dot product of a user vector and item vector, to take a dot product of 2 vectors, you need to have them be in the same dimension, right? But that's a very unsatisfying answer, because like I'm just like appealing to math. In practice, sort of, if in a lot of, certainly in places like Netflix that, have a lot of hardcore machine learning people working full time on this problem, you can do something like sort of you're doing some deep learning system where you can take in two vectors and then like ultimately you'll output some prediction given those two vectors, or like given entire ratings history, like entire interaction histories for the user, and then like something similar for the item. And there, yes, you could have arbitrary dimensions combined in like weird ways. Any other questions? Okay. So why do this? Why am I like emphasizing matrix factorization besides the fact that it's like just used everywhere? So what's nice about this is we don't need to guess what features matter. So if you remembered, so I mean, it's been a while, so I'll remind you. We taught two other, high-level approaches, item-based and user-based filtering, where what we did was we said two items are related to each other if they share the same director, they share the same actors, or they're the same genre, or whatever, right? We defined some distance metric that said two items are similar if XYZ is true. Or we said two users are similar if XYZ is true, right? They share the same demographics, or whatever have you. And the big problem with that approach is you need to like have a very strong understanding of what makes two items similar, or what makes the preferences of two users similar, right? Like you need to know that people like movies by genre or something. And you need to exactly know how people trade off having the same genre versus having the same director versus having the same release date and so on, right? So that's a lot of manual like feature engineering on your part for exactly what matters. And like you probably don't have great insight on how comparatively each of these things matter. And what's nice about matrix factorization is you don't have to do any of that. Like all you do is you take the ratings matrix and you let the system learn like implicitly what features matter, right? So we never told the system that like The Incredibles is a children's movie and whatever Blue, I don't know what that is an adult movie that's like an artistic movie, right? We never told the system that, but it learned to place the movies on this two-dimensional grid, and then someone came in and post hoc labeled, this axis looks like a children's axis, this axis looks like a blockbuster axis, right? But this all automatically happened. So that's really nice, and because of this, people have found that just like that matrix factorization techniques tend to have very good predictive power over like hand-engineered features. On the other hand, now you need historical data per user and per item. And so if you sort of what I talked about in collaborative filtering, or sorry, in item-based and user-based, is for item-based recommendations, if I'm saying that two items are similar to each other, if they have the same genre or actors or what have you, then if a new movie comes in, a new movie's released, I know all of those features about that movie, right? Like I can look up on IMDb what all of those features are. And then I can immediately provide recommendations for that movie to users without having to see any history for that item. And the same thing for user-based collaborative filtering is, I can use whatever their profile or the internet cookies or whatever have you to get sort of features for that user, like demographics. And then if a new user comes in and I have features for that user, I can just, even before they watch a single thing on my platform, I can give them recommendations. And so maybe not in a place like Netflix, but a lot of you might end up working at like smaller retail shops, or places that don't have as many repeat customers as like something like Netflix or Amazon does. And so those approaches are really helpful in how to do semi-personalized recommendations immediately for someone new before you observe any data about them. And we don't have that in matrix factorization. Matrix factorization doesn't let you do that because you need data on each user and each item. It's also hard to provide explanations. So I talked about this on the last slide a little bit, is they're like, we post hoc, because it was 2 dimensions, we're able to label what we thought the 2 dimensions were. But in reality, if you're using 300 dimensional vectors and things can be rotated in this 300 dimensional space, whatever have you, it's hard to extract, this dimension means something, that dimension means something else. And there's a lot of active machine learning research on exactly this. By exactly this, I mean in general, from like embeddings-based or deep learning-based models, how do you extract explanations out of it? And it's a challenging problem.
You have to refactorize every time you get a new item.
Oh, that's a great question. So the question is will you have to refactorize every time you get a new user and item and you see a bunch of data for that user and item? And the answer is yes or no, yes and no, in the sense that like you want to refactorize because sort of those additional rows and columns will maybe help you do predictions for other rows and columns, right? And sort of not just with new users and items, but existing users and items just get more history. And so you want to use that to update your system. So you certainly want to. There's a lot of work on, again, I don't want to touch on training too much, but it turns out you don't have to retrain the entire system with more data from scratch. You can actually iteratively train such that you have new data comes in. You can very efficiently update your vectors with using just the new data without having to touch the old data too much. I mean, there's limits to how effective that is and so on, but there's really nice ways to do that. And so it can certainly be much more efficient than factorizing a matrix of millions of items and millions of users every time.
And is that the same when user actually use the product and give a true rating over the predicted?
Yeah. So the question is can I also do this updating in practice efficiently when I just observe more entries in the matrix? Yes.
Has anyone ever done a comparison between these items and user-based methods and the matrix-based methods? Because I can understand how preferences on music or movies or art based on environmental data are difficult to engineer around, but something like a job or something like item, one coffee maker, you want to spend $12 on it. That's kind of what you want to spend on it. Has there ever been a comparison on how these things work for across different sort of genres of?
Yeah, great. So the question is, I mean, I'm going to paraphrase the question a bit, is do different methods work well for different applications? So you could imagine in movies, I really don't know what makes someone like a movie, but for a product versus like a coffee maker, maybe wealth very much does correlate with whether I'm going to want a $10 coffee maker or a $1,000 coffee maker. And yeah, so I think that's 100% true that in different applications, each of these methods have different strengths and weaknesses, and in different applications, you're going to want to use different ones. I don't know if I've seen a comprehensive it's like a single blog post or a paper that says in this genre this works, in that genre that, or in this application this works, in that application that works. I think for a few reasons. One is to write a blog post like that, you need experience in all those applications, and it's hard for one person to get that. But I think maybe the second reason, and I'm going to go into this in I think the next slide, is that in practice you can also combine the different techniques. So you can use matrix factorization based techniques for users that you have a lot of data, and then use that to bootstrap recommendations for new users or new items. And then once you get enough data on the new user and new items, then you can sort of gracefully switch over to using something like matrix factorization. And I'm going to actually ask you to do almost exactly that in the homework. And sort of the conceptual part of the homework walks you through, sort of has you go through this really cool algorithms map that Stitch Fix, which is like an online like retailer, is like an online fashion clothing box company. They send you like boxes of clothes every month, and they're probably one of the most like algorithmically sophisticated companies out there right now for their size. They probably have way more data scientists than they like need to have, but that's another thing. But so they built this really cool like map of like how different algorithms are used in each stage of the process. And if you like go to the recommendation system part, you'll see almost exactly that, where they use a combination of matrix factorization based methods and explicit features that they have about each customer.
So matrix factorization, and does it cover for interactions of features that doesn't matter much on its own, but in conjunction with another feature?
Yeah, so the question is does matrix factorization sort of allow for interactions between features such that a feature by its own doesn't matter, but like sort of in combination with another feature, it does. And so in a literal sense, it doesn't, because sort of if you're defining a feature as a dimension, so if you say that features map cleanly on dimensions, that like feature 1 is dimension 1, feature 2 is dimension 2, then like mathematically it doesn't, because you're just, you know, taking the dot product, and so you're summing like the multiplication of each feature independently. But it does in the sense that there's no reason for the system to learn that features map onto dimensions like that, right? Like dimension 10 could be like sort of the interaction between two features, right? So dimension 10 could be, is this a children's movie and a children's artistic movie, like children's animated movie? And in that sense, it can certainly learn these interactions, and it does. That's just like in linear regression, sort of, I think a confusion a lot of people have with linear regression is you can have a feature, like sort of, let's say you have a covariate, like a continuous covariate, and you can put it in as a linear regression as just like that covariate x1, right? You can also put as like in your training data, you can just square that covariate and like have another column that's x1 squared, right? That's still linear regression. That's still going to sort of, you're going to learn a coefficient on x1 squared. It's still linear regression, but you're now learning that sort of the square of that feature matters for prediction, or x1 times like x2, right? You can add that interaction term in linear regression, and and then you can learn that there's a coefficient on x1 times x2. And so similarly here, that can like implicitly happen with multiple features.
You know, in practice, it's hard to understand what some of these dimensions are representing. Is there an ethical concern kind of evaluated maybe some of the features and all waiting on things that
but that's a really great question. So the question is especially if like recommendations are like black box, like you can't interpret why I'm recommending someone to something, then why, like sort of what happens if there's like correlations that you don't want to learn, right? That like either race or ethnicity or wealth or something that you don't want your recommendations to be correlated with that. And like 100%, that's like a problem in practice. I actually have a recent paper on basically exactly that. And sort of the question, like sort of, unfortunately, like it's a very hard problem, and like just like getting like just auditing that system is hard, and then like doing something about it is harder. So and I think that's especially bad news for something like sort of not just when you're doing recommendations, but when you're also doing like adding pricing on top of this, right? So like what if I like sort of now like sort of add like pricing on top of this, where I change the price depending on how much I think you like or need something. And if that now correlates with, you know, demographics or wealth or things that you don't want it to correlate, now suddenly your system is discriminating on things that you don't even know about. That's certainly a hard problem. I'm gonna, I think, dedicate a lecture to that in the pricing section in a few weeks. Any other questions here? Okay. Yeah, so in practice, these are used when you have enough data. Okay, so I think I talked about this a few questions ago. So what happens when you don't have a lot of historical data on some new users or some new items, right? So you have, you do have a lot of data on historical purchases by some users, but then a new customer comes to your site. How do I do recommendations for that new customer? Or how do I do recommendations for a new product on, like, in your catalog that you haven't seen anyone buy yet? This is what's called the cold start problem. And so how do you tackle this? The idea that I'm going to talk about today is you just combine it with item and similarity-based recommendations. There's a few other tricks you can play, but sort of this is the basic idea I want to cover in this class. So how do you do that? So the first step is, and we're going to have you do exactly this in the homework. So the first step is you can train a matrix factorization model with the data set that you do have. And in the homework, we're just going to give it to you. And then in step 2, for new users, find their nearby users using like predefined covariates that you have. So for new users, use user similarity-based recommendation on top of matrix factorization. And I'll talk a little bit in detail, like how you can do this finding step. But yeah, so for new users, just find the closest user to them by demographics or any other data that you might have for that user. And then for those users, just pretend that the new user's user vector is the same as those nearby users that you found that did have a lot of data. And then over time, once you like start seeing like specific data for the new user who came in, update their user vectors using their personal history as opposed to like the vector that you found using their demographics. And in this way, you can have all of the benefits of matrix factorization, but then still do something for new users. Yeah, exactly. Yeah. So the question is, what do I mean by update? And yes, so I mean, yeah. So there's like, use some incremental calculation process to like find the user vectors for themselves, or like I think even more naively, you can think about sort of once I have enough data for them, add a row in the matrix with their data, and then retrain the entire system, right? So and then instead of using the vector that's found by like the neighboring users, use the vector that the system outputs for that user.
Sorry, when you say nearby, you mean like literally like right next to the district?
Oh, yeah. So what do I mean by nearby? I'm going to talk about that in the next slide. Okay. Any other questions here? Okay. Yeah. So how do you determine nearby users? And so this is where you need to do the same thing that what we were talking about in user similarity-based recommendations, right? So for nearby items, for new items come in, you can use data that you know about, right? Like use data like genre. For new users, you can use things like demographics or internet cookies or whatever you have. And this is where like your judgment needs to now come in, is you need to sort of construct the thing that a few slides ago I said was hard to construct. That like you need to use your judgment in the domain to say that like this dimension matters, but that dimension doesn't matter. No, I think so.
So I'm just like trying to actually like look for my items users. So it would be if you're looking at like nearby users, you're looking at like that matrix structure, actual matrix, and then looking at like one row, which you don't really know that much, and then you're going like you're basically like searching the rows where like the difference between like item and belief, right? Or you actually use like some sort of like
Yeah, so I'm going to talk about that in just detail in the next slide. Yeah.
So the broader question about recommendation systems, but if you're using user data, like for example, the age, gender, and to recommend items, so wouldn't this be creating like a homogenizing effect? People who are similar to you about other things.
Yeah, so that's a great question. So the question is if I'm doing recommendations, either like explicitly in user similarity based recommendations and using like demographics like gender and race, or and actually this is what I was sort of my new paper was sort of I just worked on is like even implicitly the system is learning that this correlates with that the preferences correlate with gender or race. Does that have downstream implications for what items you are recommending to who? And like certainly it does. In Amy's guest lecture, she's going to talk a little bit about these like more societal like downstream consequences of recommendation systems. But like I mean, yes, exactly, right? Like sort of these these algorithms are not like neutral in like their implications for like who they're recommending what. Any other questions yet? Okay. So, and before I dive into detail on how to do the step two, I want to emphasize that this is a key idea in a lot of machine learning settings, not just recommendations, where when you first don't have individualized data, you can pretend that someone is like an average user, or maybe pretend that they're like an average user with their covariates. But then as you learn, as you get more and more data for that user, you can try to like gracefully switch to doing more personalized things for that user. And this is like something that like sort of like this is a very common pattern to do in a lot of systems. Okay, so let's really dive into how to do this step two. So let's pretend that we have a demographic vector for each new and old user, right? So let's pretend for every user in my system, we have age, ethnicity, gender, income, whatever. Then, like one thing you can do, and I think this is the bonus sort of, I mean, I said this is simple here, but in the homework, I even defined an even simpler one now. But like in the bonus, we ask you to potentially do k nearest neighbors. But so, you can simply find k nearest neighbors based, sorry, does anyone need me to explain what k nearest neighbors is? Everyone good? Happy to do it. Okay, cool. Okay, so the simplest thing is use k nearest neighbors, right? So you can define a distance function on the vector of demographics. So I say age 1 minus age 2 squared or times 5 or whatever, right? Like define a distance function on this vector of and plot age minus age 1 squared plus ethnicity, whether it matches times 10 and blah blah blah, right? So define some distance function on this vector of demographics. And then for each new user, simply find the k closest old users in your data set. So I have, 1,000 users whose history I already have, and I also have demographics for them. And so out of that 1,000, for each new user, I just find the k nearest users in that database according to the distance function you defined on the vectors, on the demographic vector. And then I just take the average of those k user vectors, right? So I have user vectors for each of the And sorry, so here I want to be clear. I want to distinguish between the demographic vector for each user and the user vector you learn from matrix factorization, right? Those are, I want to make clear that those are two distinct things. You have like a database of demographics for each user, but then that, are probably interpretable. And then you have this vector that goes, that like this d-dimensional vector for each user, that for each old user that you learned from the matrix factorization for that old user, right? And what's nice is that we, or at least in this example, we're going to pretend that we have demographic vectors for every user, both new and old. But we only have this d-dimensional user vector, latent factor vector for old users. And so we find the k closest old users, and then we just average their vectors, right? So take the average of each dimension. And then, from that average, we get some d-dimensional average vector. Sort of, does anyone want me to go through that in a different way? Was that confusing? Yes, yes, average their latent vectors, right? So the average of dimension 1 is 10, the average of dimension 2 is 5, and so on.
But we're running KNN on the interpretable demographic.
Yes. Exactly, right? So you run KNN on the demographic vector, and you can do that because you have or we assume that you have the demographic vector for every user, both old and new. But then, so let's back up. So what's the goal? The goal is to come up with a latent vector for the new users. And you don't have enough data on what they like to come up with a latent vector for the new user. And so that's what we want, a latent vector for the new user. You have demographic vectors for the new users and the old users. And so you run k nearest neighbors on the demographic vectors. And what that outputs is, here are the k old users who are most similar to me. And when I have the k old users who are most similar to me, I can take their latent vectors because that's what I have in my data. And then I can take the average of that and use that to construct the latent vector for the new user. Yeah, exactly. Yeah. So there's like a lot of challenges with doing KNN in practice. Hopefully you're covering some of that in applied machine learning, which is, like, how do I find K? How do I find the distance function? Like defining the distance function here is not a neutral choice, right? If I say that the distance function, really values income, like, two people share the same income, that's like going to affect the recommendations I make for good or bad, right? So you should be like, well, one, you should know that you want that to happen, like you want income to matter. And two, you should have some guess that income matters for the thing that you're recommending. Okay, so that's one simple thing. In the homework and the bonus part, I'm going to ask you to sort of implement like k nearest neighbors. In the mandatory part, so earlier this used to be the mandatory part, but after homework 1 feedback, I made it the bonus. So now in this even simpler part, the mandatory part, what I'm going to have you do instead is just like the very simple, you can think about it as KNN, but like a very simple take, split, there's a column called wealth, split that into 2, high wealth and low wealth based on the median, and then just average all the vectors, all the latent factor vectors for the high wealth old users, and average all of them for the low wealth old users. And then use those 2 vectors as your new user vectors for any, like whichever one of those 2 is appropriate for any new user who comes in, right? So you could, that's like a, for example, one-dimensional version of k nearest neighbors. Let's ignore that. Okay. What you could also do is you can train matrix factorization with a known user vector as opposed to an unknown user vector, right? So in the approach that I said earlier, I said is you don't know user vector U's for each user, and you don't know item vectors V for each item, right? And then you train the system such that you're simultaneously learning both. But what you could also do is you can train that system such that you pretend you already know the U's for each user, right? So you can just say the user vectors for each user looks like this. And then the only thing I'm training is the item vector for each item. And that actually turns out to be an easier optimization problem because you already like assume you know half the answer. And you can initialize and you can set that user vector based on demographics, for example. Okay, so there's a bunch of other approaches you can use. You could also like sort of like plug in a machine learning model here and like or any machine learning model here instead of k-nearest neighbors, right? So you can use some old you can use any function on the demo, like any machine learning model where the data, the covariates are like the demographic covariates, and the thing that you're predicting is each dimension of the user vector, right? Like you're trying to predict dimension 1, right? That's a well-defined machine learning problem. You have a single target, or you have D different targets, but you're going to train D models. So you have, dimension 1 of this user vector, and you're training a machine learning model using all the covariates that you have, like all the like demographic covariates you have for each user. And then you train D separate models, one for each dimension of the user vector, and then you construct the vector that way, right? That's just like replacing k-nearest neighbors with D-independent machine learning models. Or maybe you can couple the machine, like, you can use some machine learning model that outputs in multiple dimensions. Does that make sense? Any questions? Yeah, exactly. So like one thing you can do is a regression, right? So the target of the regression is the first dimension of the user vector. And then the covariates are all the demographic covariates. You can run a regression. And you can train that regression based on the old users that you have. Because for the old users, you have their demographics and you have the first dimension of their user vector, of their latent factor vector. And then you can train a regression on the second dimension of the latent factor vector and the third dimension and so on. Any questions on that? Yes. Yes. It's just.
Like you'd have to somehow know dimensionality of
Yeah. So the sort of this entire setup is assuming that you have latent factors for a bunch of old users, right? And you also have demographics for those old users. And now the problem is a new user comes in and you want to do recommendations for that new user, right? And so for a k-nearest neighbor model, you need those latent factors for the old users, right? Because that's what you're going to average for the new user. And this machine learning regression approach, the same thing. You need training to train such a model. You need training data from old users for who you have both demographics and latent factors. And then you want to predict then you're going to use that model on the new users who come in to construct a preliminary predicted latent factor vector for them. And then once you have enough data, you can replace it with their own latent factor vector. Yeah, well, yeah. So in the original approach, the UIs were the latent factors that you were learning.
Yeah.
But in this new approach, that you can do is replace the UIs from the unknown latent factor that you're learning, and just replace it with the known demographic vector for each user, right? So now you have a known demographic vector for each user, and instead of training a matrix factorization model such that you're learning both the latent factors for the users and the items, you're pretending you know the vectors for each user based on the demographics. Yes, it'll be the dimension of the demographic vector. And then you're just going to learn VJs, which is how now it's going to be how the how the movie space maps onto the demographic space, right? So, for example, movie is going to have a really high first dimension if, like, let's say the first dimension is age, right? So it's going to have like a really high first dimension if elderly people like that movie. It's going to have a really negative first dimension if children like that movie. Right, and so this also tends to be interpretable as well. And if you sort of dig into that Stitch Fix algorithms tour that I linked to in the homework, you're actually going to see that they do a combination of this approach and sort of like pure latent factor approach, where they're learning sort of where in their system they like set some dimensions to things that they know about the user and learn automatically other dimensions. Any other questions here? Oops. Any questions at all on the prediction part of recommendation systems? Okay, so what I thought would be the majority of this lecture, but no, and this is great, y'all are asking a lot of questions, but what we're gonna start on today and really dig into next time is, so you have prediction, right? So like now for the rest of the recommendation system model, or the module, I'm going to assume that you know how to do prediction, that you know that you have a filled in matrix of how much you predict each user is gonna like each item, right? And then now the goal is to sort of do something like with that prediction, right? So like once you have predictions, like predictions aren't enough to recommend things, right? Like you ultimately need to show people these are the 10 items I want you to watch, or these are the 10 people I think you should hire, and so on, right? So how do we go from predictions to like doing something about it, recommendations? And I think this is what the part that, even though like a lot of machine learning classes call it recommendation systems, they sort of stop here. They stop at the prediction part. When I think the claim is in a lot of the platforms that y'all might end up working at, sort of what to do with the recommendation, what to do with the predictions, how to actually turn that into recommendations is as hard of a problem as getting the prediction right. And so that's where we're going to start on today. And I think the homework actually focuses on this one. Okay, so what's the most naive thing you can do? So you can train a matrix factorization model, or like, you know, do any of the prediction stuff that we just finished, and just pretend that I have predictions for each item in each user. And so I'm just gonna, and then, you know, then I've, you know, this prediction, I have a filled in matrix. And then for each user, just simply recommend the item that I predict them to like the most, right? Simply recommend to them that, like, you know, if, you know, and if, you know, I sort, you know, I have predictions for all 1,000 items for each user, and then for each user, I just sort and then take the top item and recommend it to that user. Or if I'm doing sort of recommending K different items to each user, then I sort and just take the top K, right? That's simple. That's probably like the first thing most people would do, right? Any questions on like the simple thing that I would do? Okay. So like, clearly that's not what I would recommend that you do in practice. And so what are some issues? Actually, before I get into issues, I'd love for people to like sort of what do y'all think is wrong with this approach?
I guess like all the items, they could be grouped into different categories. So there's no like differentiation between like other variables, like maybe like interactions. Because it's just a high level like overthinking.
Yeah. So one issue is, you don't just want like sort of the max over all possible items. Maybe you want like Netflix doesn't know right now if I want to watch an action versus a romantic comedy versus whatever, like an animated movie. And so maybe instead you should take the max over like different genres, right? So you should, and this is somewhat what Netflix does is they show you a screen and they give you like 5 different rows, and then they label each row with like action, romantic comedy because you like XYZ, and then they fill in sort of not exactly, but like, one thing that you could imagine is they take the max on each dimension, on like each of those different dimensions. Yeah, so that's one issue and one possible solution. What are other issues with this method?
Let's say I'm on Amazon and I buy a vacuum, and now my whole feed is filled with vacuums that I don't need, but I've been associated with some user that likes to buy vacuums.
Yeah, that's a great one, which is that, and this is especially common in products, is sometimes you buy or consume an item and you're like done consuming that item forever, right? Like I don't need to buy vacuums every month. But sometimes I consume items and that's indicative of I need to like continuously buy those types of items every month, right? So like diapers or books or like consumables, right? And so how do you distinguish, how does a platform distinguish between those two things?
This could be like raining on popularity. So if you have like either a niche taste or like popular,
Yeah, so the claim is if you don't just like the most popular item, like you have niche taste, and maybe you're not serviced by this. And I want to say that's both true and false. Where like in theory, what you just said is false. In theory, my user vector could be like highly personalized to my niche taste, and this argmax is based on my user vector, right? It's the prediction on what like me, Nikhil likes. And so if I have niche taste and they do a good job learning the user vectors, then like in theory, they'll show me according to my niche tastes. Now in practice, you're exactly right. And we're going to look at that in the homeworks where like, because of like artifacts of how these things are trained and because of like limitations on data and so on, that actually does exactly end up happening that sort of like popular items get sort of, if you think about a dot product or like, the sum of taking multiplications, there's two ways something can be high, right? One is if your two vectors are pointing in the same direction, so you're aligned sort of like, this is exactly the taste that I like. Another way it could be really popular is if I just have like that vector has a really high magnitude, right? If all of the elements are infinity, right? Then, well, you have to worry, let's not worry about sign issues, but like sort of if all the dimensions are infinity, then like I'm like, it doesn't matter if I'm pointing in the right direction as you, if I'm pointing anywhere and like similar to you, you're gonna have a really high relationship. And so, yeah, so in theory, what you said is not a problem. In practice, it certainly is.
this is a question. If we have like a perfect mapping between like the preference and the rating that's given, would the would this naive method not good predictions or good recommendations?
Yeah, so the question is like, if I did a really, really good job with the user vectors, then like, isn't this exactly the right thing to do? My claim is no, and I'll give the reasons why I think that's true in the next slide, but sort of I'd love a few more. from the like, yeah, I guess, does anyone have an answer to, like, suppose I did a great job on the user vectors and the item vectors, right? Suppose like they were handed down to me from wherever things get handed down from. And like I did, like my predictions are perfect. Would I still then use the argmax? Or like, can someone explain why even then that would be potentially a bad idea? Yep. So okay. So one sort of potential thing is there, like maybe sort of, let me interpret that in the context of the question I just asked. Is like maybe there doesn't exist this like single best item that I'm really gonna love, right? Maybe there's, behavioral economists have spent the last 60 years studying this, which is like maybe there's context effects, right? Like maybe the fact that they showed like item 5 makes me like item 1 more, or makes me like item 1 less, or so on, right? So maybe there's interaction effects for like what I end up watching because of the set that they showed me. And there's a lot of actually research right now and like how to take insights, or research, but also just like building systems in practice on how to take those insights from behavioral economics that like studies effects like that into like real world recommendation systems.
I suppose one issue is how we're kind of, I guess a distinction between what would be the best recommendation and what would be the most likely to result in a purchase or like an engagement.
Yes. Okay. So one claim, which is again sort of interpreted in the context of my question, is maybe there's like no single rating that's like matters for like different things I'm going to use it for, right? Maybe there's one rating for like what I just enjoy to see the previews of on my Netflix screen. There's like one rating for like what I'm going to watch today. There's another rating for like watching this today makes me more likely to cancel my Netflix account next month, right? So there's different there's different meanings for like ratings, and the platform needs to decide which like objective that it actually cares about. Or I think, sorry, I saw that answer.
You still have an issue with like recommending like either things outside, potentially new things outside your preference, or like monitor changes.
Yeah, so that's a great one, which is that, like, again, like in practice, these ratings are going to be based on my past behavior. And so if I past like always like binge watched like trashy reality shows on Netflix, but like, I'm going to cancel Netflix if I keep like binge watching those, and instead they should show me documentaries, and like I won't cancel Netflix, then sort of this approach will fail. Right. So it traps people into being recommended what they previously like. Any other sort of problems with this? Yep. Yep. So the answer was is there might be capacities to each item, right? Like a restaurant can't serve everyone on the same evening, and so if I recommend everyone go to that restaurant, then quality is going to suffer. I might just have only 10 items in my warehouse. I might just have 10 copies of this item in my warehouse, and if I recommend it to everyone, then I'm going to run out of the item, right? And so that's exactly what we're going to talk about today. So what if you only have five copies of item J, but everyone likes item J? So that's the first thing, and the homework is going to focus on this, and we'll maybe introduce talking about this today, but we'll get into it, I guess, a week from today because of the guest lecture on Monday. You could also have multi-sided preferences. So in recommendations like freelancing marketplaces where workers are matched with clients, or dating apps or volunteer platforms, or a lot of places where there's people on both sides. You don't care about just how much item I likes item J, or like customer I likes item J. What you care about is how much person I likes person J, and how much person J likes person I. And so you have two-sided sort of preferences, and those preferences might not be mutual, right? Like one side might really like someone on the other side, and it might not be reciprocated. And so your recommendations should sort of take that into account. Someone talked about challenges in recommending sets of items, right? So one of the challenges is the behavioral effects that we already talked about. Another challenge here is you might care about the diversity of items that I recommend, right? So sort of this Netflix genre thing was a great example, where if I just sort and recommend someone the 10 best items they think they're gonna like, they might all be action movies. And maybe I'm just not in the mood to watch an action movie right now, even though on average I love them. And so if like what Netflix cares about is the probability that I'm gonna watch any one of the 10 movies they recommend to me, then maybe they care about diversity a little bit, where like they show me a few comedies, a few actions, and so on. And we're not really gonna talk about that in detail. In this class, we're gonna really focus on the first one, kind of talk about the second one, and then not really about the third one.
I don't know if this is an issue for Maggie in general, but what if your recommendation system takes into account liking and disliking the post you downvoted?
Yes, that's a great question. So, I think this sort of goes back to some of the data challenges that we talked about recommendation systems. Is like, so the question is what if you sort of sometimes you can like something on these platforms, like indicate that you liked it. Sometimes you can sometimes they don't let you indicate that you don't like something, right? Like on Spotify, for example, sort of I think they have a dislike button. I forget, but like they don't. Okay, someone's telling me Spotify doesn't have a dislike, right? And so you can imagine if they have a dislike button that like really helps them, like that could help them curate the feed, but there's some data reason, some product reason that they don't have one. But other platforms might allow you to both sort of express negative preferences and positive preferences, and you can certainly deal with all of that when you're designing the data, sort of the data matrix for your recommendation system. Yeah, so that's a great question. So the question is how do I evaluate that my recommendations did well? And I think this is something that a lot of platforms today are struggling with. And there's a lot of research on how to sort of do this better. But essentially the idea is there's some things that I really can measure immediately, right? Like Facebook can measure how long you spent on the website today. Netflix can measure whether you continued watching this and binge watch this today or not. Then some metrics that you might actually care about are a lot harder to measure, right? Is Facebook destroying society because of polarization, or is Netflix or what you ended up watching, you disliked it so much that you cancel Netflix next month, right? And in some sense, those are the metrics that you actually care about, or maybe should care about. But it's easier to measure these instantaneous metrics. And so how you train recommendation systems to optimize those long-term metrics is a hard problem, and something sort of a lot of people have put in various tricks. Maybe you can get proxies for sort of the issue with a lot of those long-term metrics is the data doesn't come in until a month from now, and you can't attribute it to a single watch, right? If I cancel my Netflix account, I didn't tell them because it's because of these 5 things. I just canceled my account. And so how do you attribute it to specific recommendations decisions they made? So that's a hard problem, and there's various tricks people try to pull in practice to to tackle it. Okay, so these are all great. So I'm gonna sort of introduce the capacity issue. I won't have too much time to go into it, but yeah, sort of, I do want you to remember at a high level, sort of this takeaway that like, it's not enough, and this is true for the entire class, it's not enough to have predictions. Like what you do, like deciding what to do with your predictions requires probably more thought than like plugging in a machine learning model to get good predictions. And like it's important, and like choices that you make here like matter for different objectives that you have. Okay. Clearly, this is not what we're going to cover today, given there's like 3 minutes left. Okay. So let's just like introduce dealing with capacity constraints. So what's the challenge exactly? So let's, I'm gonna maybe introduce what I think might seem tangential, but I promise you is related. So some of you, maybe the few of you with CS backgrounds sort of might have been introduced to something in algorithms called maximum weight matching in a bipartite graph. Like, don't be scared, like, that's a lot of words that you might not know, but like, sort of, I'll like introduce it slowly. And then we're gonna claim that like, in the case of capacities, where we can solve this easier problem or this more exact, more optimal problem. And then we're going to try to get insights from solving that easier, more optimal problem to real life applications. Okay, so in the last minute or two, I just want to like formalize what the challenge is. So let's say in many settings, you're recommending items with capacity constraints. So, you have a finite number in your warehouse, and Airbnb can literally only be booked by one customer at a time. On a labor market, workers can't work for every client simultaneously, and a client is probably, has a finite number of people they're going to hire for their job. People on dating apps can't talk to everyone. Then, sort of, if you ignore these capacity constraints, then like bad things are going to happen, right? Like everyone's going to be recommended the most popular, like, or some items are going to be recommended more than they have capacity for. And then when you go to actually make a purchase, someone's going to be left disappointed, right? So like if like, 2 people are being recommended the same exact Airbnb for the same date at the same time, then like only one of them will be able to actually check out. Or the same for, where items in your warehouse. And so the question is how should you factor in capacity in your recommendations? And the challenge is trickier because you might also have the future to take into account, right? So if I only have 3 items in my warehouse and I know like I can't get another shipment for the next 2 months, then it's not just have to worry about the current customer who's in, but also any potential customer who will be able to come in for the next 2 months, right? Like maybe there's a customer who's really going to love this item, but they don't come in until next month. And so how do I like take into account those that potential customer when I don't know that that potential customer exists? So I think that's all I have. I'll stick around for questions. If you came in a little bit late, I did do announcements at the beginning of class. Please like watch the recording and like take care of the announcements. I think most of those announcements I also posted on EdStem.